Hey guys, what's up? This is the 9th tutorial for your linear algebra course, and I guess recently haven't had any assignment to do, just because Klaus is really busy because the math department is basically down a man at the moment. So no reason to complain because you're not getting assignment, but hopefully you will still come to the tutorial and learn. And in fact, in this tutorial, if you already watched the last video, most of problem 1 is already done for you. And then you can watch me do the optional problem 2 if you want. I don't know. But let's get started anyway. So, this first problem here. Alright, we've already looked at this plane here in tutorial 8. And we looked at it in GeoGebra and stuff, and hopefully you got a good idea of what the hell I'm talking about. Now, for part A here, what I want to show is that the plane itself is a subspace of R3. So the first thing I want to do is just write this strictly, so not lazily. So specifically, the plane P, alright, this plane, it's going to be the set of all x1, x2, and x3, such that are subject to the condition that x1 minus x2 plus x3 is equal to 0. Okay, so this is how we write it strictly. And we want to show this in a subspace. So the question is, subspace? Well, we have to show two things. We have to show that x plus y should be in the plane if x is in the plane and y is in the plane. And the other thing we should check is that lambda times x is an element of the plane if, again, x is an element of the plane and lambda is any real number. Okay, so here are two things we have to check. And the easiest way to do this would be, well, if I take x1, x2, and x3, and I add y1, y2, and y3, then this is going to give me, and just don't specific here, this I'm just going to pick to be any element x that's in the plane. I shouldn't do my stuff sideways. X in the plane, this is y, and it's in the plane. And we want to check that the resulting vector, x1 plus y1, x2 plus y2, and x3 plus y3 is in the plane. So how can we check that? Well, we need to check that this condition is held for this vector here. So if I take x1 plus y1, which would be our x1 coordinate, I take away the x2 coordinate, so minus x2 plus y2. And finally, I take x3, the x3 plus y3. And I want to make sure that this is 0. So I don't know what's 0 just yet, but hopefully we can show this. So collecting all my x terms together gives me this. And collecting all my y terms together gives me this. Plus, I know that x is in the plane. So I know that this thing here has to be equal to 0. Similarly, I know y is in the plane as well, so this has to be equal to 0 as well. And so x1, or sorry, and so this vector here has to be an element of the plane. So that implies x plus y is an element of the plane. So we've checked the first guy here, this one, and now we just need to check the other one. So lambda multiplied by x is an element of the plane. This should be easy enough. So if I do lambda times x1, x2, and x3, that's the same as lambda x1, lambda x2, and lambda x3. And I want to check if this is in the plane. So take our x1 coordinates, subtract the x2 coordinates, and add the x3 coordinates. And I want to check that this is equal to 0. Well, the first thing I can do is factor out a lambda from everything. x1 minus x2 plus x3. Exactly like this. And again, I know x is in the plane, so this thing has to be 0. So it's lambda times 0, which is 0. Therefore, lambda x in the plane. And we've checked both of these conditions here for the plane to be a subspace. And so that's part A done. Now, part B is not too bad, but I would recommend that you think about it a little bit. So, what property do you need to have a basis for a subspace? And you should know that, firstly, that a basis is made of linearly independent vectors. Right, linearly independent vectors. So whenever you have a basis, okay, a basis is the minimum number of vectors you need. So you always just throw away your linearly dependent vectors before you make your basis. And so if I take a basis of, vectors v1, v2, so on and so forth, and maybe we have k different vectors, that means all these vectors should be linearly independent, which I write as lin ind, linearly independent. And what other condition do we need? So we have this condition here, that they should be linearly independent. But what are we making a basis of? We're making a basis of pi, the plane. So the basis should span pi, the plane. Right, i.e. the span of all of these should give me the plane exactly. No more, no less. And these are the two things we just need to remember when we're looking for bases of subspaces. First thing you know is all bases are linearly independent. So you got to check that first. And then, well, not first, but you got to check that. And also your basis should span whatever it should be a basis of. So if you're looking for a basis of OR3, your vector should span OR3. If you're looking for a basis of a line, your vector should span the line, so on and so forth. The next part of B was to figure out how many vectors you'll need to find, or sorry, how many vectors you'll need to span the plane. Okay, so we did this in the last tutorial where we actually found what the vectors were, but just to give the answer without doing anything hard, here's R3. And now if I draw a plane in R3, right, it might look something like this. Call it pi. Obviously, a plane is a two-dimensional space, right? It's a 2D, like a sheet of paper, okay? Two-dimensional. So you should only need two vectors in your basis in order to span pi. So k is equal to 2 for the plane pi. I.e., only need two vectors. Hopefully that makes sense. Like, I mean, obviously, the plane is a 2D thing, so it's two-dimensional. That's fine. But the point of linear algebra is to get rigorous with that. What do you mean by dimension, right? What do you mean by basis? What do you mean by spanning? All these things are important because soon enough, we're not just looking at planes in R3. We're looking at, you know, subspaces of functions in function spaces. And that's kind of what the optional problem in this problem that's going to be hitting us. But for now, let's move on to part C. And I actually did do part C already, right? Find a basis B for the subspace P. Okay. If you want to go watch tutorial 8, you can. I'm also just going to do it out here because I feel like people are having trouble with finding bases for certain things. So let's find a basis for this plane here. Okay, so I'm going to write out my formal definition for pi again. Pi is the set of all vectors x1, x2, and x3, such that x1 minus x2 plus x3 equals 0. So I find a basis by trying to change the form of this set of things. And again, I talked about this even more in tutorial 7 and the common mistakes thing, because a few people weren't able to find bases for a plane in the first homework assignment. So here this is like a condition, right? And here just the set. So it's a set of all 3D vectors, but this condition has to be satisfied. What you want to do when you find a basis, not always, but most of the time in linear algebra, is you want to try and take the condition and plug it into here. Okay? Changing it to so-called parametric form. But this is, I guess, besides the point. I'll show you how it's done. And if any of you are interested, obviously you can go watch. So what we do is, before I even write equals there, if I have x1 minus x2 plus x3 equal to 0, this is one equation, one x, two unknowns, two unc. Sorry, one equation, three unc, three unknowns. And that implies that there's two degrees of freedom. Okay? So I can take two variables here and let them be whatever I want and still have this equation satisfied. So I'm going to rewrite this as x1 equals x2 minus x3. And then I'm going to say let x2 be equal to t t any real number, and let x3 be equal to s any real number, and that means that x1 is going to be t minus s. Okay, so after doing this work, right, I identified how many variables I'm allowed to just let be anything. It's 2. And because of this, I can now plug into here what x1, x2, and x3 are, and get rid of the condition over here. So now this looks like pi equals set of all, and now x1 is t minus s, x2 is t, and x3 is s, such that t and s are real numbers. Okay, so we've changed this from set builder notation to parametric form, and then the last step is to just break this vector apart. Right, because t is a real number, I can just factor it out of this vector. T is multiplied by 1 here, 1 here, and 0 here. And then add s, again I can factor it out because it's just a real number. I have a minus 1 here, and 0 here, and a 1 here. Again, t and s should be real numbers. Okay, so now we have the basis. We have the 2 vectors in our basis for pi. Because, alright, the plane pi is going to be the set of all linear combinations of these vectors. Okay, so I can take this one and multiply it by anything I want. Let's say t is 5, and then I can add this vector and multiply by anything I want. You know, let's say minus 3000, and all of these vectors, right, as I vary t and s to every single different value, it'll give me the entire plane pi. So these 2 vectors are a basis for pi, where these 2 vectors span pi. So the span of 1, 1, 0 and minus 1, 0, 1 is equal to pi. Okay, if you want a little bit more detail, you can check out the last tutorial in problem 1, or you can check out tutorial 7 in the common mistakes section, where I do a question like this. I explain it just a little bit more. And that's part C done. And part D, pretty fine. Find the coordinate vector x in the basis of B of the vector 3, 1, minus 2 in pi. So x is 3, 1, minus 2. D x is 3, 1, minus 2. And I want to find x in the basis of B. And remember, B, our basis, is just going to be these 2 vectors. 1, 1, 0, and minus 1, 0, 1. Okay? So, x, we can break it apart, right? Let's say we took say we took our first vector 1, 1, 0, and we added to it, or maybe we subtract from it the other vector, and I put in a 2 here. Then I think you can check 1 minus 2 times minus 1 is 1 plus 2, which is 3. 1 minus 0 is 1. 0 minus 2 times 1 is minus 2. So this works. And so if I call these vectors here v1 and v2, then I can see this is v1 and that's v2. And so x is going to be 1 times the vector v1 minus 2 times the vector v2. And so x in the basis b is going to look like 1 minus 2. Okay? So just extra explanation. Hopefully this basic stuff is making sense to you now. But the reason x in the standard basis, right? If you want to think about it, there is actually a basis for x here. It's the standard basis that you write like that. Usually we just ignore it. So if there's no basis specified, it's usually just a standard basis. But we're just being explicit here. The reason it looks like 3, 1 minus 2 is because it's 3 times e1 plus 1 times e2 minus 2 times e3. You know, we build the vector out of how many of each e1, e2, and e3 we need to make it. So down here, if we choose a different basis of v1 and v2, in our basis, we might as well represent the vector as how many of each v1 and v2 we need. And so that's why the answer is what it is. And that's problem 1 done. Right, pretty fine. I feel like I ranted a little bit too much, but if you're confused about anything, again, please go to the last tutorial. I drew the plane and everything, and I was talking about that for a good while. So if you're confused, hopefully that'll help out. And so we're going to move on to the optional problem now. Gee, I'm all over the place. All right, here we go. So we're going to read this. I'm not going to give the answer for everything, but I'm going to try and help people if they want to do this, to do it. So we can just basically ignore this. All right. We don't need to explain what baby calculus is. Right. Start here. Let V be the vector space of all real valued functions f of the form f of t in some constant times sine, some constant times cosine, some constant times sine of 2t, plus another constant times cosine of 2t. And then we have dv, which is the differentiation operator. And what dv does is when you apply it to a function, it gives you back the derivative of the function. Okay? Not too bad at the moment. And then at the very bottom, we let g1 be sine, g2 be cosine, g3 be sine 2t, g4 be cosine 2t. So part A, we want to show that g is the basis for v. Well, again, first thing you have to check is g linearly independent. So is g linear independent? Well, you're going to have to do you're going to have to check that the only solution to this equation is 3 sine 2t 4 cos 2t, and let this equal to 0. You want to check that the only solution to this equation for every value of t is that a1, a2, a3, and a4 are all 0. But then g will be linearly independent. How would you do that? Well, you need to look at specific cases. So I'll do, I guess, 2 of them. If you take t as 0, okay, remember, this equation has to work for every value of t. So you can just pick values of t, sub them in, and see if they work, and get equations out of it. So t equals 0 means that I'm going to get sine of 0, cosine 0, sine 0, cosine 0. And I know that sine of 0 goes to 0, and the cosine of 0 is 1. So I get a2 plus a4, which means that a2 is minus a4. And then we need to find another equation. So let t be equal to pi over 2. And so the sine of pi over 2 is 1. Cosine of pi over 2 is 0. A3 times the sine of 2 times pi over 2 is sine of pi. And the sine of pi is actually 0. And the cosine of pi is minus 1. So I get 0 equals a1 minus a4, which implies that a1 is equal to a4. And so on and so forth. You can let t be equal to pi over 4, pi over 8, so on and so forth. And you just plug in, and sometimes your sines will disappear, sometimes your cosines will disappear. And you should get multiple equations. You only need 4 of them. And then when you sub each of these equations into each other, right, you can just do simultaneous equations or row reduction now that you've learned this. But you'll get that all the a's have to be 0, which is what you want. So that's how you do part A, to check if they're linearly independent. And now we need the basis part, basis of V. So the second thing you need to check is that the span of G, right, or I guess G1, G2, G3, and G4 is equal to V, which is kind of trivial. Okay, so every vector in V looks like a linear combination of sine, cosine, sine 2t, cosine 2t, and the span of these vectors here is going to be every linear combination of them. So obviously the span of G is the same as V. For part B, we're going to now look at bases or bases in questions that are no longer or 1 or 2 or 3 or 4. We're now looking at function spaces. So how do I find the coordinate vector hg of the function h of t in 3 sine t minus 7 cosine of t? Well, h is 3 sine t minus 7 cos t. But in the basis g, sine of t is g1, cosine of t is g2. And then I can throw in the zeros for my g3 and g4. You don't have to, but they're implied. And so we can write that in the basis of g, the h is going to look like 3 minus 7, 0, 0, like that. I have 3 of g1, I have minus 7 of g2, 0 of g3, and 0 of g4. Okay? So hopefully that makes sense. And then if f is just a random function, right, it's going to look like a1, g1, a2, g2, a3, g3, a4, g4. So we can write f in the basis of g as just a1, a2, a3, and a4. Not bad at all. Okay? If you want me to explain a little bit more about what's going on here, I mean, I guess it is confusing. We're going from functions into somehow vectors. But it's all to do with the basis, okay? It's all to do with the fact that G and the basis hide all these functions, which just gives us the G1, G2, and G3, which then we can use to create basis vectors. And so we can write stuff as vectors. Okay. So part C then is to find the coordinate vectors of dv of h and dv of f. Remember, dv just means to take the derivative. All right. So let's do that. Let's start with h, and you should be able to do f on your own. So h is 3 sine t minus 7 cos t. And so if I were to differentiate it, sine goes to cosine, as much as we know, and cosine goes to minus sine. So I get this. And therefore, dv of h in the basis of g is going to look like 7 of sine of t, 3 of cosine of t, and 0 of sine 2t and cos 2t. Okay? So you can do this very easily again with f. You just plug in what your genes are, differentiate, and it should be grand. Let's see. So how do you do part D? What even is part D? So part D is find a 4x4 matrix to represent differentiation in the basis of G. So I should be able to find a matrix such that instead of doing the derivative like I do every time, I could instead just multiply by a matrix. So how do you do this? Remember, to make a matrix, you need to look at what dv done to basis vector. So dv of g1 is cosine of t, g1 is sine of t. dv of g2 we know it's minus sine t. G3 is sine of 2t. So all that happens here, you get an extra 2 out the front because of the chain rule, and the cosine of 2t here. And G4 is cosine 2t. Very similarly, we get minus 2 sine 2t. And so this is what d does to the basis vector. And this makes more sense if I write cosine of t and g2. Minus sine of t into minus g1. This is 2 g4. And this is minus 2 g3. Okay? So the matrix is going to be made out of, the columns of A are going to be made out of what D does to our basis vector. But what it does to the first basis vector G1, it sends it to G2. So I have 0, 1, 0, 0. So first column is just G2. Second column here is minus G1. So I get a minus 1 up here for G1, 0 everywhere else. The third column then should be given by 2G4. So I get 0, 0, 0, 2G4. And finally, the fourth column is going to give me 0, 0, minus 2, 0. Okay? And this is your matrix. It's done differentiation for you in this particular vector space. And then we move on to part E. And part E then to show that the matrix is invertible and find its invert. I'm actually going to leave this off because it's a 4x4 matrix, and it, you just have to do row reduction. Hopefully you should be able to do this. If any of you are having trouble with finding inverse matrices, right, row reducing to the identity, just send me a message. I'll go through a few different inverse instances and see if we can make it a bit more clear what's happening. And then part F asks, is there a linear transformation D inverse such that D inverse of F equals A inverse of F for all F in V? Okay, and the punchline here is that in part A, if you try and invert it, you find that A is invertible. You can find what A inverse is because it exists, and because A inverse exists, then for part F, D inverse of V exists. So remember, dV was represented by A, and if A inverse exists, then A inverse is going to represent some dV inverse. And you can find both of these, and I encourage you to. But I think that's all there is to do today. Or actually, I forgot to mention the punchline of this. So for this particular problem, we find the right punchline, most important part. Differentiation can be represented by a matrix. In the vector space C. Okay, and we do it, and we find that there's an inverse and whatever, and has a valid inverse. But remember, V is just made out of sine t, cos t, sine 2t, and cos 2t. So it's a really small vector space. It's 4-dimensional. It's, it's certainly not every function that we can think of. It's a very small subset of functions. And so the question is it possible in general to do this? So is it possible for any type of function I want to come up with a matrix that can differentiate it, and then invert that matrix to find the invert differentiation method, right? i.e. integration. So it's possible in general to do, right, this. No, it's not. Okay, so consider V V subscript new. So this is going to be a new vector space. It's going to be our normal V, but I'm going to add to V a new thing, which is going to be just a constant. And so any vector in V new is going to be the set of all A1 sine t plus, I'm just skipping there, A4 equal 2t plus a5 such that all of the a's are in OR, right? This is my new vector space. It's got this a5 here, but I know that if I do dv new onto some function f, it's going to get rid of this a5, right? It's going to dv new will get rid of a5. If I differentiate a constant, that just gives me 0. So I have that a5 is going to be in the kernel of dv new always, right? a5 is always going to disappear when I apply dv new, and that means that the kernel of dv new is going to be the set of all a5 such that a5 is real. And so the kernel is actually just going to be 1D real space. And that means that my kernel is not 0, which means my map can't be surjective or injective as it goes, which means that I can't make an inverse. Okay, remember, to make an inverse map, it has to be surjective and injective, or bijective. But here I've just shown that if I add even just a constant function to my vector space, that immediately my differentiation map is no longer invertible. So that's the punchline. In our idealistic world where all functions look like they're in B, then we do have invertible differentiation. But in the real world, when we have to deal with things like constant functions, we find differentiation is never invertible, right? And this is why when you integrate something, you have to add the plus c, or you have to solve the condition given on the bound to the integral, yada, yada, yada. Now that's me done. I should have assignments 5 and 6 corrected by next week, and then I'll get on to correcting the exam. If any of you want me to go through the exam again, you need to just email me or message me on Canvas. I don't really care. So I'll see you next week for the next tutorial. And if class puts up an assignment, I get to do it, but you probably don't need to worry about that.